Let's learn how to initialize big data sets to make a good training and to make backpropagation get going. The weights of ANNs must be initialized as small random numbers as investigated by Goret and Benjio in reference 3.5 in this book. You can read these books for further information. The Goret and Benjio forced the variance of the weighted sums to be smaller, and hence the variance of the weighted sums of inputs connected to a given node of neural outputs at a layer z. In any hidden layers, under considerations. Then what's going to happen is that your variance is going to be reduced to some number. The Goret and Benjio forced the variance of weighted sum to be smaller, and hence the variance of the weighted sums connected to a given node of neural outputs at layer z is reduced to 1 over m. See, if your variance reduced by 1 over n, then your weights then should be reduced square root 1 over n, because the weight square right now constitute the variance. The weights of different neural links square to calculate variations. So if your variations is reduced by 1 over n, then your weights or neural links of different neurons from previous layers should be reduced square root 1 over n. That's easy to understand. So that the n denotes the number of weights or number of neurons, number of weights. So now same is number of neurons connected to the nodes of the previous layer. This mitigates decaying or vanishing and the exploding gradient issues. So we see that if we have a large neural values around here, it's gonna go and vanish your gradient of activation function, which in turn causing a vanishing or decaying problem. Or if that is big, then it's gonna cause exploding problems during backpropagations, hindering your training process. So this is something you should prevent from happening. In order to shift the variance of the weighted sum of the neural outputs at a layer z from 1 to 1 over n, as you see over there, weight variance is reduced 1 to 1 over n. Each weight is multiplied by square root 1 over n. Again, n is number of weights or as a neurons after being randomly generated with the zero mean and variance of 1. Various weight initialization techniques have been suggested other than this. Now we're going to take a look at a little example how we're going to apply this theory to reduce your neural values at layer z in any hidden layers. Try to calculate your gradient which do not vanishes, so that your backpropagation get going to improve your training process for enhanced weights and bias calculations. Okay, let's take an example. Let's assume that you're going to use 2 over n formula. It could be the formulas that is presented by the Goret and his, and we're going to explain why I'm using 2 over n instead of 1 over n. It really doesn't matter. Those people proposes a different formulas for different activation function and different type of distributions. So now in this particular example, for a variety of understanding the initializations, I'm using 2 over n to reduce variance, so that if you use a 10 neurons or 10 different neural link, so I'll say neural link. This is terms that I like. Neural links means weights. So neural link is mostly linear, isn't it? Linear, as we see many times in earlier lectures. So that if you use n equal 10, then 2 over n becomes 0.2. Therefore, knowing that the variance is function of w squared, so that you have to go and calculate w by applying square root of this value, which is 2 over n. So that you need to reduce the wn all the way to wn by multiplying these factors, right? This is very easy. Square 0.2 is multiplied to original weights where your weights are, you think it is too big, right? We try to reduce the weights and try to reduce the variance to get back propagation. This is weighted sum of z. So you go and multiply this and this, this and this, this and this. You weight it by weights, and sum of it is be the input or output at z-axis in all hidden layers. This is why I say weighted sum. You could say weighted sum of input. You could say that input, the weighted based on neural links, which is weights. Okay, and in this way we succeeded to reduce variance. So when you reduce variance, as we know that the variance is gonna go and get skinnier, right, than before. If you see over here, you go and get skinnier again, right? So you're going this way, so by multiplying weights here. So let me try to say again that widely spread weights cause widely spread variance and standard deviation that hinders back propagations, and weight shrinks variance and standard deviation if you decrease or reduce weights by this ratio. If you use a 1 over n formula, now we having a example have a 2 over n formula. It could be any formulas. That's why I'm taking these formulas. But I'll show you in second that there's a many formulas, a way of doing initialization based on your distribution of big data, or activation functions. The people like Xavier, and he presented very nice initialization way. As you see in these diagrams, the randomly generated weights there are around 0 with a variance and standard deviation of 1 are multiplied by square root 1 over n in these diagrams, but we see the same example which is reduced based on 2 over n. Okay, don't get confused. I gave you a couple of examples. You can use 2 over n. You can give and calculate 1 over n, and based on your distribution and activation function, it is all different between method. So you can use this, you can use this. Just I gave you the example based on 2 over n. But anyway, your big data are based on any distributions. Could be uniform distributions or uniform normal distributions. So you have to take a look at what kind of distribution you have in your big data to choose a proper factors like 2 over n, 1 over n, things like that. Also, the activation function type will affect your selections. the randomly generated weights are around 0. It means your mean of randomly generated weights, or all neural links, the mean of all neural links are 0, and you have a variance which is reduced here, as you see, by whatever factor you use here, and standard deviations, and that is going to be multiplied by, say, 1 over n or 2 over n to variance, or square root 1 over n or square root 2 over n to weights. Okay, this is what happens. It's easy to follow, isn't it? Okay. The new variance of the weighted sum makes the distribution of the weights centered around 0, but with significantly smaller variance, either 1 over n, as you see in this figure, or 2 over n, as we see in our sample calculations here. It really doesn't matter. Rather than the distribution of weights with a variance of 1. Means that your original weights has a variance of 1, with the original weights. But now a new variance reduced to 1 times 1 over n or 2 over n, The reason I'm repeating this is that this is not only factor you can use, or this is not only factor neither. So you can use any factors, but it depends on your selection based on your distribution of data and activation type again. Right? So you can reduce the variation with the new weights. Okay, follow? Easy? Okay. The weight initialization process must be performed on per layer basis. All hidden layers must have processed with this initialization if your initializations is required, especially when your neural values are pretty big here, so that you vanishes your gradient of activation functions, and you will kill the back-propagation processes and hindering updating your weights and bias. Okay, now let's take a look at initialization. I'm trying to introduce some of the very important formula for initializations, and this section is based on 3.2 from Taylor and Francis. I wrote this book in English version as well, so you can take a look at it and refer any part you need to. And the Xavier's method for initializing weights are summarized as follows. Okay, so you can use a uniform distribution functions, which works very well for sigmoid activation functions. So usually the Xavier is specialized in presenting a initialization method for sigmoid and 10H mostly, and one of the way of doing initialization for a uniform distributions, again this is for sigmoid uniform distribution. He has two ways here, uniform distribution. So first way is to use only input neuron number right there, and so n is a number of weights coming into a given neurons, and out denotes a number of weights going out of these neurons. And this is a one of simplest method. So that if you have this as a standard deviations, then your variations is going this guy, isn't it? Okay, so that your variation is this, and you consider the n in and out, which is a number of weights coming into a given neurons, and out, which is number of weights going out of these neurons. And you have a little bit different formula, which was modified from the previous one, and you're having it here. Again, your variation is this. because your standard deviation is written as this formula as you see over there. So these are very similar to one that is presented in first cases. And what if we have normal distributions which has zero mean and also works well sigmoid? A sigmoid for this for the normal distribution functions, your standard deviation is this. Therefore, you're having a variance of this. So this is a very similar one previously presented by himself. But there are, and if you have 10H activation function, if you use 10H activation function, you're going to use this formula again. This is figures. So 1 over n as variance if your standard deviations are this, right? So here we have a formulas for normal distributions for each sigmoid and 10H, and we have a different formulas, but not much different. They are very similar. You wanna recall that when necessary. Okay, now let's take a look at for ReLU activation function and LiqReLU activation function. He is the name. He proposed a method for initializing weights and variances for ReLU activation function and Liqi activation function for normal distributions both and a uniform distributions. For normal distributions of the big data, he has a zero mean of course and standard deviation of this, where then your variance becomes 2 over n. This is what we have seen in our examples in earlier slides. So this is very simple to understand what you do with these factors. This is also proposed by he for ReLU and Liqi for normal distribution. Okay. If you have a uniform distributions, the similar factor has been proposed when your uniform distributions function has a zero mean and standard deviation of this, which is leading to your variance of this. All right, this. Okay. So they are very similar, this and this, but interestingly, these factors are fixed for ReLU activation and LiqReLU when you have normal distributions and a uniform distributions respectively. And also the MATLAB has its own default initialization method, which is developed by Ng Withdraw. So very nice initialization method that the MATLAB is adapting, and you're going to see this references for that. And the ANNs they use in neural network toolbox by MATLAB uses a default initialization method proposed by Ng Withdraw layer initialization method, in which each layer weights and biases are initial. Okay. So the network is trained with the Levenberg back-propagation scheme, so that given input and output parameters learn to match the associated target outputs with the minimal mean squared error. And this is very important information that you're going to use this when you use a MATLAB as a default, but you can still change your initialization to see sensitivity or influence of your initialization on your training result. You can use here the Xavier's and he's and something else, and always good to check if what kind of initialization works better for your system, because your system is unique. It is from other data that the people is using out of your lab.